Here it says evaluate at the inside, which is e to the x plus e to the y, times the derivative of what's inside. What is the derivative of e to the x with respect to x?
E to e?
Nope. E to the x. E to the x is its own derivative. And what is the derivative of e to the y with respect to x?
0.
0. Because anything that just has y, if y is a constant itself, so I'll say y is 3. This is e cubed, which is like 2.718 cubed, it's a constant. The derivative of this with respect to x is 0. And I'll tidy it up a little bit. We get e to the x divided by e to the x plus e to the y. We'll just leave that there for a second. Now we'll calculate the other derivative, partial derivative.
Could you not calculate it out?
There's not much more we can do with it really. Are you saying do something with this?
I thought we could calculate out from each
Cancel, we can cancel.
Yeah.
I'll just show you what you can do. So just be wary of this cancelling business. Okay, so I'll show you a few things you can't do. So e to the x plus e to the y. So one way of cancelling might be saying you somehow get 0 over e to the y. Okay? Another way might be e to the x over not equal to e to the x plus e to the y. Another kind of, it's not equal to 1 over 1 plus e to the y. There is something we can do, but it's not actually helpful. We'll explain that in the last one last. How do you get from e to the x to 0?
Divide by 2? No.
No.
Multiply by 0?
Yes. Is there another way? So, okay, how do you get e to the x plus e to the y? Subtract itself. Can you take away above and below?
Yes. No.
Can you take away above and below?
No.
No. So that one is gone. That doesn't work. How do you turn e to the x into 1? Divide by itself. Now, can you divide above and below by the same thing? Can you do that?
Yeah.
Yes, you can. How you can do it is you can divide by 2 by multiplying by half. What's that red joke equal to? What's that equal to?
0.5?
No. What's that equal to? 1. Multiplying by 1, you get the same thing. So 8 by half is 4, 6 by half is 3. You can do this. Did we divide above and below by e to the x here?
We did, yeah.
No, I didn't. If I was to do that, I'll do it here. So you get 1 over e to the x, 1 over e to the x. That would be dividing above and below. So e to the x divided by e to the x is 1, fair. E to the x divided by e to the x is 1, fair. But when you are dividing a sum, you have to divide all of them.
Okay.
So you get plus e to the y divided by e to the x, which arguably is nicer. Now there's little you can do 1 plus e to the y minus x if you really want, but there's no need. Okay. So I'd say be careful with the cancelling. Okay, so we'll do this other one. So we're differentiating this partially with respect to y. We've got an outside and an inside. The outside is log. What's the derivative of log of x? 1 over x. Evaluated at the inside times the derivative of what's inside. What is the derivative of e to the x with respect to y? 0. What is the derivative of e to the y with respect to y?
E to the y.
E to the y. So tidying that up, we get e to the y over e to the x plus e to the y. Now I'll add these together and I'll use a slightly different notation. I'm going to use zx, that's because we're going to see this a little bit later on, I'm going to use this. So that's the same as this, differentiate z with respect to x, plus differentiate z with respect to y. Let's calculate it. We get e to the x divided by e to the x plus y, excuse me, e to the x plus e to the y, plus the derivative with respect to y, which is this, e to the y divided by e to the x plus e to the y. What do you need to add fractions together?
Same
Denominator.
denominator.
Bottom and same, so we have that.
Yeah.
So you can add them together. E to the x plus e to the y, e to the x plus e to the y. Just like say 2 sevenths plus 3 sevenths is 2 plus 3 sevenths. What's this yoke equal to?
1.
Does it satisfy the partial differential equation?
Yeah.
Yeah. That's the kind of thing you could see. You can extend this, as I said, to more variables. Don't think we'll see it, but yeah, we'll just leave that off, okay? I'm not going to examine it. It just works. It works. Pardon?
They won't examine the NV, yeah.
No, I wrote that example. It just works in the same way. If you want to differentiate with respect to x, keep y and z constant. Okay? And just x changes. Right. Now we need to hire, if you want to differentiate, find second derivatives. Here's a question. How many second derivatives do you think there are? There's 2 first derivatives, the way we've done it. How many second derivatives? 4. Yeah, because you can, yeah, very good. We'll show that to the rest of us. So let's differentiate this with respect to x and with respect to y. So say partial z.
Maybe can I butt in there for a
You
second?
can.
Sorry. You know where you have the actual function to start the log of e to the
Can you
x
do
to
something
the
like
y?
that?
Yeah.
No.
No. What I was going to say was,
Okay.
when you don't have x in the question, anything in a bracket, can we take that as x? That looks like what you've done there. When you differentiated the log of x, you made what was in the brackets x. Is that standard across the board for everything we do, like with all the rest
That's
of
the chain rule.
Okay.
So I would have said log of x, yeah.
All right, okay.
So really what I'm saying, okay, so the general version of what I'm saying is if you're differentiating, so I'm going to write u of v, right? That's like this. So what I'm doing is, so the outs, it's difficult to name the, see, what I want to do is, I don't really want to say what's the derivative of log. Like log on its own doesn't actually, it needs an input. So I'm just putting, now I'm all saying x, like I could say u, I could say v. I think if the way you might have done the chain rule last semester, which I'm not mad on, doing that like the way I'm doing it, you'd say what's the derivative of log of v? What's the derivative of log of v? 1 over v. And actually that actually kind of, it does give you what you need, because the chain rule says you differentiate the outside, you differentiate the log, and then you evaluate at the inside. So actually that wouldn't be the worst way to do it actually. And then you multiply by the derivative of what's inside. You're giving me something to think about there. Yeah. So, I think I might do it like that in future actually. Yeah, okay. Yeah, thank you. Did that answer your question?
Kind of, but yeah.
No, it does answer your question. The x is just a placeholder.
Yeah.
It's just so I can't just say log. I need to say log of something.
From last term, if I was looking at that, I would have started differentiating the everything except that way. You know what I mean? It just seems to be kind of coming slightly together. I'm just wondering, was I?
You might have du dv dv dx, and I'm not a fan of it because if the dv dx needs a chain rule, you're just in pain. So I don't like it that way. It's not wrong. It's fine. I just like if it can be a double chain rule, and I think you can get completely lost. That's what I think. Okay. So coming down here, so again I'm going to call the derivative zx and zy because that is what we're going to be using in the next section. You need to be comfortable with the two really. So zx, differentiate this with respect to x. So in the first term, what is the constant with respect to x? Sine y. If y is a constant, so is sine of y. And what is the derivative of x with respect to x? 1. Plus. What is the constant in the second term with respect to x? Y. What is the derivative of x squared with respect to x? 2x. I'm going to tidy this up. This is sine of y plus 2xy. We'll also differentiate this with respect to y. Going back to the start, in the first term with respect to y, any constants about? X. Fix the x. What is the derivative of sine of y with respect to y? Plus y. Any constants about in the second term?
X squared.
X squared. Everything that isn't y is a constant. X isn't y, so x squared is a constant. What is the derivative of y with respect to y? 1. So we have x cos y plus x squared. So you very quickly, and in fairness, I asked the day class and they never get, when I say how many second derivatives, a lot of you got it straight away, there's 4, because this can be differentiated in 2 different ways, and this can be differentiated in 2 different ways. So strictly there's infinitely many second derivatives, because it's just a question of pick this direction, then this direction, there's loads of pairs, but we're just going to do x and y. So both of these partial derivatives are again functions themselves, so you can differentiate them again with respect to x or with respect to y. So what we'll do first is, and we'll confuse us with the notation, I'll try and keep. I'm going to switch to the other notation. You need to be comfortable with both, right? So I'm going to switch. So this we're going to differentiate with respect to x again. Now how we write this is differentiate twice. Now we've done the first one. We're differentiating z and we're differentiating with respect to x twice. So this thing here means differentiate twice with respect to x both times. We've differentiated once with respect to x. We've got a schematic to explain this if you're a little bit lost in the next bit, in this bit. So differentiate once with respect to x. We want to differentiate this again with respect to x. What is the derivative of sine of y with respect to x?
0.
0, because if you're going with respect to x, everything with y is a constant, so y is maybe 2. So sine of y is sine of 2, which is a constant derivative, constant 0. Any constants about in 2xy with respect to x?
Y.
Y, anything else? 2. So 2y. And what is the derivative of x with respect to x? 1. So that's 2y. We'll put it in the diagram down below in a moment. Okay, so that is twice with respect to x. Now let's do maybe over here. I can't remember which one it's supposed to be. It doesn't really matter. Yeah, this one should be first x and then y. Now we write this a little bit funny, and I will explain why. It doesn't matter if this confuses you. We'll explain why in a moment. So if you want to differentiate here twice, so differentiate one of these again. And if you want to go first x, then y, the way you write it is, you put the x here if you want to do it first. Now, and you want to do the y second, you do that here. Now, this will be explained again, And if this is confusing, that's okay. We will explain why it's okay if you're confused. It won't matter, right? But this one, if we're doing things properly, this means with respect to x first and then y. So we've done with respect to x, we need to differentiate this with respect to y. What is the derivative of sine y with respect to y?
Zero.
No,
Cos
sine y
y.
with respect to y is cos y. With respect to y, any constants about? 2x. And what is the derivative of y with respect to y? 1. Okay. So this is x first, y second, but if you're like, what are you on about? That's y, and then the x, just chill a second. Now we'll do y first, then x, which would be written differentiate twice. First y, then x. So we're differentiating this with respect to x. So with respect to x, looking at the first term, any constants about?
Sorry, differentiate one.
So with respect to x, in the first term, any
Cos
constants?
y.
Cos y is, anything with y is constant, so cos y is a constant. And then what is the derivative of x with respect to x? 1. Plus, what is the derivative of x squared with respect to x? 2x. And we've got one more second derivative. Differentiate twice, differentiating z, with respect to y both times. So we have to differentiate this with respect to y. With respect to y, on the first term, any constants about? X is a constant, yeah. Times, what's the derivative of cos y?
Sin y.
Minus sine y. And finally, what is the derivative of x squared with respect to y?
0.
0. Now I want to explain the notation, why this means x first and then y. Sorry. Why because of y is it? WHY is this x first and then y. So say if I have a z, and if I want to differentiate it with respect to x first, I write that. And if I want to differentiate this with respect to y, I write that. And then if you kind of, where this notation makes sense is you kind of multiply them together. Now it doesn't make sense, but that's what the notation means. Partial by partial, partial squared, differentiate twice, and you see you have the x here and then the y. Now the joke is, if that confuses you, does it matter? Can you notice anything about the second derivatives?
They're the same, really.
These are the same.
They're the same, yeah.
Yeah. 2x by 1 is 2x, cos y by 1 is cos y.
Would they always be like that?
There are really weird examples where that doesn't happen. You won't meet them. And I don't mean you won't meet them in the test. You won't meet them in engineering, pretty much full stop. Pure maths course, you can come up with stupid ones where it doesn't work. I actually can't explain it. I don't really know what it is, so it's like, yeah. I get my head in a knot, but basically what it is you're looking at the, say the first one, you're looking at the slope in the x direction, and you're saying, how does that slope change as you walk along the y? And somehow that's exactly the same as if you look at the slope in the y direction, how does that change when you walk in the x? I don't know why they should be equal. It's more than a coincidence, but I don't know exactly why it is. Right, now what we're going to do is just, if you're a bit lost on that, we're going to put all the functions on this thing, and hopefully you'll have a better picture then. So we'll come back at 25 past.